More electrostatics. The hits just keep coming. What we're going to do in this one is we are going to sketch some electrostatic field lines, which you should know how to do, but we're also going to put in some equipotential surfaces in there. You may have done this with gravity before, but if you haven't, try and make it make some sense. And there's a relationship between those surfaces and the field lines. Hopefully you'll find that easy. And the IB doesn't tell us to, but we're going to look at how electrostatic equations also relate to gravitational ones. To draw these equipotentials, we've got some electric field lines set up that you should be familiar with. Here's some capacitor plates, and these pink lines are showing that you've got uniform electric fields going through there. And what an equipotential line is it's a line that along that line everything is at the same voltage or the same potential. And so let's draw one of those in. We're going to make it dotted, and we're going to make it red. So if we go all along here, everything along here is the same potential. If we put another one, everything along here is the same potential. And here, and here, and here. And traditionally you draw these so that the difference between them does show as you go from one to another, the voltage is changing and getting lower, and maybe this is 5 volts, maybe 4, 3, 2, 1, until you get to 0. Now if you do that around a point charge like this, then it's going to be circular. Everything on this circle will be the same voltage. And as we go out here, everything along here will be the same voltage. And now we should make these a little bit wider as you get out. Because let's say maybe you're at, I don't know, 10 volts here, and then 9. To drop down to 8, you're going to have to go farther, and then maybe we'll go up to 7 volts here. But the key is everything along this circle is at the same potential. And let's say we've got a negative point charge, and we want to draw equipotentials. That won't be a problem. You just do the exact same thing. Because if you, let me make this purple. If you draw a circle around here, everything's at the same potential. Draw another one. Everything around here is the same potential. And the next one you would need to draw out here. And actually this looks just like the equipotentials that you would draw around a planet for gravity. It also has its field lines going inwards like this negative point charge. If you have a positive sphere, conducting sphere, let's say it's hollow, inside it would have no field and thus no need to draw equipotentials, but then outside your equipotentials would look exactly the same as if it were a point charge. Circles, and they get farther spaced as you go around. Now, a couple important things that you should remember is this, that wherever you go on this equipotential line, you're showing that the concentration of these field lines is the same. The other thing you need to know is that these equipotentials are always perpendicular to your field lines. Always, always, always. And so let's compare all of these electrostatic equations to their kind of gravitational counterparts. So let's say that we have the force due to electrostatics here. With gravity, you have also force due to gravity. Instead of this K, you've got big G. Instead of these charges, you've got masses. And just like over here, with distance squared, same here. Now this is in newtons. This is also measured in newtons. If we look at electrical field strength in this equation, we also have gravitational field strength, which we usually use small g, and you might think of as the acceleration of free fall that might be on a certain planet. The equation, though, is similar. Instead of K, big G. Instead of charge, we've got mass, and it's over distance squared. This, for electrical field strength, is in newtons per coulomb. Here, it's going to be in units of newtons per kilogram, or also in meters per second squared. If we are looking at electrical potential, we also have gravitational potential. And you'll see the same parallels. Instead of K, big G. Instead of charge, mass, and it's over the distance. This will be in units of joules per coulomb. This will be in units of joules per kilogram. And with here, the electrical potential energy. It's a little confusing because it's still an E, but this is electrical potential energy, not field strength. Over here, we've got gravity potential energy for gravity, and just before we've got big G, two masses, and we've got over the distance. And just like this, since it's energy, it's in joules. This is energy, it's also in joules.